Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body start releasing the weight of the day. If this peaceful journey is already beginning to slow your thoughts, consider subscribing now, so these stories can keep finding you night after night. And now, let the relaxation settle into your breathing. The planet you live on has 4.5 billion years of history. And for almost all of that time, it would be completely unrecognizable to you. There would be no air to breathe, no familiar landscape, nothing you could call home. And yet, here we are. And the more we look, the more remarkable that becomes. The Earth's early atmosphere was a mixture of methane, ammonia, and carbon dioxide. Not a single molecule of free oxygen. What we breathe today is largely the result of billions of years of biological activity. It wasn't planned. It happened slowly, invisibly, cell by cell. And what that reveals is something that changes the way we see the world. The climate has never been fixed. It's a system in dynamic equilibrium, always adjusting. The stable climate that human civilization has known over the last 10,000 years is, on a geological scale, a remarkable exception. Not the rule. There's something deeply strange about that. All of our history, all of our architecture, all of our agriculture, all of our understanding of how the world works, was built within a climatically exceptional window of time. A window that wasn't guaranteed. That simply appeared. And there's a detail that changes everything once you start to understand it. About 700 million years ago, the Earth became almost entirely covered in ice. Scientists call this event Snowball Earth. The ice reached regions close to the equator. A state that, by any current standard, would be an unprecedented catastrophe. The planet survived because of volcanoes. Even beneath the ice, they kept releasing carbon dioxide into the atmosphere, gradually warming the planet over tens of millions of years. It was that rescued the Earth in that moment. What's curious is that the very same substance that once saved the planet is now at the center of one of the greatest concerns in modern history. The difference isn't in the mechanism. It's in the time. Back then, the process took tens of millions of years. What's happening today is occurring on an incomparably faster scale. And that brings us to something most people have never heard of, the Great Oxidation. About 2.4 billion years ago, microscopic cyanobacteria began releasing oxygen as a byproduct of photosynthesis. In quantities large enough to irreversibly alter the composition of the entire atmosphere. For the organisms that dominated the Earth at that moment, that oxygen was poison. It was, in a sense, the first great environmental crisis in Earth's history. Caused by living organisms. Not by geological forces. And that matters because it demonstrates something scientists take very seriously, the atmosphere can be radically transformed by biological processes. What's happening today is analogous, but reversed. Now, it's the activity of a single species that's altering the balance of the air that covers the entire planet. Let that idea settle for a moment as you breathe slowly. A single species, transforming the atmosphere of an entire planet in a fraction of a second in geological terms. About 300 million years ago, the Earth was covered by dense, humid forests that stretched across entire continents. It was the Carboniferous period. These forests absorbed enormous amounts of carbon dioxide, and when the trees died, they simply accumulated. There were not yet organisms capable of fully decomposing them. Layer upon layer, for millions of years. That material became coal, oil, natural gas. The fuels that humanity began burning on a large scale with the Industrial Revolution. In other words, fossil fuels are carbon that was pulled out of the atmosphere hundreds of millions of years ago. Burning them reverses that storage process in the blink of an eye, in geological terms. And what almost no one realizes is that this carbon wasn't available by accident. It was stored over immense eras, through processes that took longer than our minds can imagine. We're releasing it in centuries. The asymmetry between the time it took to accumulate and the time it takes to release is one of the most unsettling things about this story. There's a Serbian mathematician named Milutin Milankovic who, in the early 20th century, discovered something extraordinary. He realized that the Earth has astronomical cycles that influence its climate over periods of tens of thousands of years. Variations in orbit, in the tilt of the axis, in the direction the axis points. These cycles, known as Milankovitch cycles, are directly associated with the ice ages that the Earth experiences periodically. And according to these astronomical cycles, the planet should be entering a period of gentle natural cooling over the next tens of thousands of years. The warming we're observing today goes in exactly the opposite direction from what the astronomical cycles would predict. That's not a coincidence that goes unnoticed. It's one of the most compelling reasons why scientists conclude that the current cause is distinct from the natural climate variations of the past. The last major ice age ended approximately 11,700 years ago. During that period, much of the northern hemisphere was covered by ice sheets up to 3 kilometers thick. Sea levels were about 120 meters lower than they are today. Large areas now underwater were solid land. And it was precisely during that climate transition that the first human civilizations began to develop. Agriculture, cities, writing. All of recorded human history has unfolded within that exceptionally stable window. Human societies were built on an unusually predictable climate. And that stability is not guaranteed going forward. This starts to get more interesting when you consider that not all climate variations in the past were slow. About 12,900 years ago, an event called the Younger Dryas caused temperatures in the North Atlantic to drop dramatically within a matter of decades. Possibly because of a disruption in ocean currents triggered by the rapid melting of ice. The cooling lasted about 1,200 years before the climate stabilized again. That kind of event shows that the climate system doesn't always behave in a gradual and linear way. Under certain conditions, it can shift states relatively quickly. It's a characteristic that scientists take very seriously when trying to understand what may happen in the coming decades. And there's a scientific tool that allows us to look directly into the past of Earth's atmosphere. Air bubbles trapped in layers of ice in Antarctica and Greenland. By drilling deep into the ice, scientists can extract air samples hundreds of thousands of years old and precisely measure the composition of the atmosphere at different points in time. The records obtained cover the last 800,000 years. What these records show is that the current concentration of carbon dioxide in the atmosphere, around 420 parts per million, has no precedent at any point in the last 800,000 years. The highest values recorded in the past, during naturally warmer periods, were around 300 parts per million. The difference is not small. And there's a detail that changes everything. Earth's climate has been much warmer than it is today. During the Cretaceous, about 90 million years ago, average temperatures were between 8 and 10 degrees higher. The poles had no permanent ice, and dinosaurs lived in regions that are Arctic today. All without any human intervention. But the fundamental difference between that warming and the current one is the pace. The natural climate changes of the past occurred over millions of years, giving ecosystems time to adapt. The current warming has no parallel in the geological record in terms of speed. And that speed is precisely what makes the ability of ecosystems and societies to adapt a central concern. As you breathe slowly and your body sinks a little deeper into comfort, think about how strange it is that the danger isn't so much in the final destination, but in the speed of the journey. There's a widely held idea that the greenhouse effect is a problem created by humanity. But that's not exactly true. The greenhouse effect is a natural phenomenon and absolutely necessary for life. Without it, the average temperature of the planet would be around -18 degrees Celsius. A frozen world, unable to sustain life as we know it. What human activity has done is intensify that mechanism, not create it. It's the difference between a blanket that warms you and a blanket that suffocates you. The object is the same, but the intensity changes everything. The sun's energy reaches Earth primarily as visible light. When it hits the surface, some is absorbed and some is reflected back into space as heat. Greenhouse gases have a specific property. They're relatively transparent to incoming sunlight but absorb some of the outgoing heat. the atmosphere acts as an asymmetric filter. It lets energy in more easily than it lets it out. The higher the concentration of these gases, the more efficient that blocking becomes. What almost no one realizes is that not all greenhouse gases work the same way. Water vapor is actually the most abundant in the atmosphere and is responsible for much of the natural warming. But it doesn't directly drive current climate change, because its concentration is controlled by temperature, not by human emissions. Carbon dioxide has a distinct characteristic. It stays in the atmosphere for centuries. When it increases and raises the temperature, that causes more evaporation, which increases water vapor, which warms the planet further. CO acts as the trigger. Water vapor amplifies the effect. Scientists call this kind of dynamic a positive feedback. In 1896, long before any computer existed, a Swedish chemist named Svante Arrhenius manually calculated, over the course of months, that doubling the concentration of CO in the atmosphere could raise global temperatures by several degrees Celsius. His estimate fell within the range that modern climate models still consider plausible. What's curious is that Arrhenius didn't see this warming as a threat. Living in cold Scandinavia, he imagined that a warmer planet would be beneficial for agriculture. The concern about negative consequences would only come decades later, when other scientists noticed the speed at which CO concentrations were actually rising. And this starts to get more interesting when we think about where that additional carbon actually comes from. Burning fossil fuels is the largest source, but it's not the only one. Deforestation is the second largest source of human carbon emissions. When a forest is cleared and burned, the carbon stored in those trees over decades or centuries is released into the atmosphere in a matter of hours. What makes deforestation particularly problematic is that it operates in two directions at once. In addition to releasing carbon, it eliminates that forest's future ability to absorb CO. It's like spending your savings and closing the account at the same time. The impact is twofold. Agriculture rarely takes center stage in climate discussions, but it accounts for between 19% and 29% of global greenhouse gas emissions, depending on how the entire supply chain is measured. The digestive fermentation of livestock, manure management, and the cultivation of rice in flooded fields are significant sources of methane. And nitrous oxide, released through the use of fertilizers in soil, has a warming potential about 270 times greater than CO over 100 years. Cement is another example that surprises people. Cement production accounts for about 8% of global CO emissions, more than aviation and maritime shipping combined. And a considerable portion of those emissions is chemical, unavoidable in the conventional process. The raw material releases CO when heated. Even if all the energy used in production came from renewable sources, there would still be emissions. Decarbonizing cement requires rethinking the process itself, not just the energy source. As you let these thoughts drift gently through your mind, notice how the world you inhabit is built on processes we rarely see, and how these silent processes shape everything. There's a concept that helps explain the depth of the climate problem. It's called committed warming. Even if global emissions drop to zero tomorrow, the average temperature of the planet would continue rising for a few more decades. The climate system has considerable inertia, especially the oceans, which absorb heat slowly and release it back into the atmosphere over decades. That's not a reason to give up on reducing emissions. On the contrary, the sooner emissions decrease, the lower the total accumulated warming will be. But it's a reminder that the climate system doesn't respond instantly to our actions. It carries memory. The oceans cover about 71% of Earth's surface, and their role in climate change goes far beyond their size. They function as the planet's primary thermal regulator, absorbing more than 90% of the extra heat generated by the increase in greenhouse gases since the pre-industrial era. Without that absorptive capacity, the warming of the atmosphere would have been much faster and more severe than what we've seen so far. The problem is that this absorption comes at a cost. The oceans are getting warmer at increasingly greater depths, and the heat stored in them will continue influencing the climate for decades, regardless of what happens with emissions. The ocean is, in that sense, both a buffer and a reservoir of future consequences. Beyond heat, the oceans absorb about 25% to 30% of all co-emitted by human activities each year. This happens through the dissolving of the gas in seawater and through the photosynthesis of phytoplankton, microscopic organisms that form the base of the marine food chain. Phytoplankton is responsible for about half of all photosynthesis that occurs on Earth, even though it's invisible to the naked eye. When these organisms die, some of the carbon they absorbed sinks to the ocean floor. It's a process called the biological carbon pump, a natural capture mechanism that has been working for millions of years and that is gradually being affected by ocean warming and acidification. When co-dissolves in seawater, it reacts and forms carbonic acid. This releases hydrogen ions, making the water more acidic. Since the Industrial Revolution, the average pH of the oceans has dropped from 8.2 to 8.1. That seems small, but it represents an increase of approximately 26% in acidity due to the logarithmic scale of pH. This acidification directly affects organisms that rely on calcium carbonate to build their shells and skeletons. Oysters, crabs, corals, certain types of plankton. In more acidic water, this material dissolves more easily. Since many of these organisms sit at the base of marine food chains, the cascading effects could be considerable. And there's a detail that changes everything in this ocean equation. There's a global system of deep ocean currents called thermohaline circulation. It works like a giant conveyor belt, transporting heat, salt, nutrients, and carbon across all of the world's oceans. A complete cycle can take between 500 and 2,000 years. This circulation plays a fundamental role in regulating regional climate. The North Atlantic Current, part of this system, is responsible for keeping winters relatively mild across much of Western Europe. If this current were to weaken significantly, the consequences for European climate could be substantial, even within an overall global warming scenario. Recent data suggests this circulation is weaker than at any point in the last 1,000 years, possibly because of the influx of fresh water coming from the melting of Greenland's glacier. Fresh water is less dense than salt water, and its entry in large quantities can interfere with the mechanism that keeps the circulation running. The current scientific debate isn't whether it's weakening. It's how close the system is to a possible more abrupt tipping point. Let your breathing slow down now, each thought arriving and passing like a wave. You don't need to hold on to any of them. Global warming isn't uniform. The planet doesn't warm the same way everywhere. Polar regions are warming between 2 and 4 times faster than the global average. A phenomenon called polar amplification. The Arctic, in particular, is transforming at a speed that surprises even the researchers studying it. The main reason is related to ice. When ice melts, it exposes the dark surface of the ocean or land, which absorbs far more heat than white ice. That accelerates the melting further, which exposes more dark surface, and so on. Ice functions like a mirror. Losing that mirror means losing part of the planet's ability to cool itself. The extent of Arctic sea ice in summer has declined by around 13% per decade since satellite records began in the 1970s. And the issue isn't just the area of the ice, but its thickness and age. The oldest Arctic ice that survived multiple summers and built up thickness, has largely been replaced by first-year ice, which is thinner and more vulnerable. A particularly warm summer now has a much greater impact than it would have had decades ago. Greenland is the world's largest island and is home to the second largest continental ice sheet on the planet. In recent decades, it has gone from a state of approximate balance to a net loss of ice that accelerates year after year. Satellite-based studies show that Greenland is losing about 280 billion tons of ice per year, a rate that has tripled compared to previous decades. What makes Greenland's situation especially relevant is the topography of the terrain beneath the ice. Much of the island's bedrock sits below sea level, in a shape that functions like a basin. As the edges of the ice sheet retreat, the ocean can push in and accelerate melting from the base, a process that could become progressively harder to reverse even if temperatures stabilize. There's an important distinction about ice that's worth understanding. The ice covering the Arctic is, for the most part, sea ice, floating ice. Since it's already in the water, its melting doesn't directly raise sea levels. The ice in Antarctica and Greenland, on the other hand, rests on land. When that ice melts, the resulting water flows into the oceans and directly raises sea levels. Antarctica alone contains about 60% of all the freshwater on Earth in the form of ice. If that entire ice sheet melted, sea levels would rise by around 58 meters globally. Greenland, completely melted, would contribute another 7 meters. These figures aren't projections for the next century. They're a way of measuring the scale of what's at stake. And this gets more interesting when you consider the behavior of mountain glacier. Unlike the great polar ice sheets, they're present on every continent, including Africa and South America, and they serve as natural freshwater reservoirs for hundreds of millions of people. They accumulate snow in winter and gradually release water in summer, functioning like an elevated water tank that regulates river flow throughout the year. The Himalayas, which hold the largest glacier outside the poles and are the source of rivers like the Ganges, the Brahmaputra, and the Yangtze, supply more than 1 billion people. They're losing mass at an accelerating rate. In the short term, the melting may even increase river flow. But as the glaciers shrink, that source becomes increasingly unreliable. The accelerated melting of today can mask the crisis of tomorrow. While the ice still exists, there's water. When it's gone, the source will simply cease to exist. As you rest and your mind grows quieter, notice how some of the world's greatest risks are invisible in daily life, happening too slowly for human attention to clearly perceive them. Permafrost is the permanently frozen ground that covers about a quarter of the land surface in the northern hemisphere. It's not just cold soil. It's a geological archive containing organic matter accumulated over tens of thousands of years. Leaves, branches, animals, and other organisms that never fully decomposed because the cold kept microbial processes virtually at a standstill. Permafrost is estimated to store between 1.5 and 1.6 trillion tons of carbon, roughly twice what's currently in the atmosphere. As it thaws with warming, soil microorganisms begin to break down that organic matter, releasing CO and methane. Permafrost shifts from being a carbon reservoir to a source of emissions. And it's one of the most feared climate feedbacks among scientists, because once it begins on a large scale, it's practically impossible to stop through direct human means. The thawing of permafrost doesn't just affect the climate. It physically destabilizes the ground across entire regions, damaging roads, buildings, pipelines, and infrastructure built on terrain that has been solid for millennia. Indigenous communities in the Arctic are already reporting houses sinking, coastlines eroding, and landscapes that their elders no longer recognize. It's simultaneously a global climate threat and an immediate local crisis. Sea level rise isn't uniform across the planet. Because of variations in gravity, ocean currents, winds, and the rebound of the Earth's crust, some regions are experiencing rise well above the global average, while others show smaller increases. Southeast Asia, the Gulf of Mexico, and parts of the U.S. East Coast are among the regions with above-average rise. In some of these areas, the problem is compounded by subsidence, the gradual sinking of the ground itself, often caused by excessive extraction of groundwater. Cities like Jakarta, Bangkok, and parts of New Orleans are sinking at the same time as the sea rises. The actual flood risk is far greater than global average data would suggest. Sea level rise doesn't need to be dramatic to cause severe impacts. Even increases of 30 to 50 centimeters can turn flooding events that currently happen once a century into events that happen once a decade. Because small increases in the baseline significantly reduce the margin of safety against storms and extreme tides. Low-lying island nations, such as Tuvalu, Kiribati, and the Maldives, are already living this reality in concrete terms. Some islands have already been abandoned. Governments of these nations are discussing plans to relocate entire populations. For these communities, climate change isn't an abstract future threat. It's an ongoing transformation that's already reshaping the geography of their existence. And there's a detail that changes everything about how we think of sea level rise. The great ice sheets respond to climate at an extremely slow pace. They take hundreds or thousands of years to build up and may take similar amounts of time to fully dissolve, even after temperatures stabilize at higher levels. Sea levels will continue rising for centuries after any eventual stabilization of global temperatures. Long-term models suggest that even limiting warming to 1.5 degrees Celsius above pre-industrial levels, the long-term sea level rise already locked into the system is on the order of meters over the coming centuries. Not centimeters. Meters. It's the kind of climate legacy that transcends any conventional political or economic horizon. Let your breathing stay calm and deep, each exhale releasing a little more tension, and letting the mind grow quieter. Heat waves are one of the phenomena most directly linked to global warming, and their behavior follows a logic worth understanding. Imagine the distribution of temperatures in a region as a bell curve. When the average temperature rises, the entire curve shifts toward the warmer end. That means temperatures that were once at the far hot end now become more common. And temperatures that were once practically impossible begin to occur with real frequency. An apparently modest increase of 1 or 2 degrees in the average temperature can multiply the frequency of heat extremes by enormous factors. Events that naturally occurred once every 50 years may come to occur once every 5 or 10 years with 1.5 degrees of warming. And once every 2 or 3 years with 2 degrees. For infrastructure, healthcare systems, and vulnerable populations, that difference isn't just statistical. Another important aspect is that warm nights are just as dangerous, or more so, than hot days. The human body needs nighttime hours to recover from the thermal stress of the day. When nighttime temperatures remain elevated for several consecutive days, the risk of mortality increases sharply, especially for the elderly, young children, and people with cardiovascular or respiratory conditions. Hurricanes are also changing. And what the data shows isn't necessarily an increase in the total number of storms, but a shift in the intensity and behavior of these systems. Category 4 and 5 hurricanes are becoming proportionally more frequent. Rapid intensification, when a storm goes from moderate to extreme in just a few hours, is becoming more common. Hurricanes feed on ocean heat. With warmer oceans, there's more energy available. Additionally, hurricanes have been moving more slowly over the areas they hit, lingering longer over the same regions and dumping far greater volumes of rain than historical records showed. Hurricane Harvey, in 2017, sat nearly stationary over Houston for days and dropped more than 1.2 meters of rain in some areas. And this starts to get more interesting when we consider droughts. Global warming intensifies them through multiple mechanisms. The most direct is increased evaporation. Higher temperatures draw more moisture from the soil and plants, even when precipitation stays the same. The second involves changes in atmospheric patterns that alter where and when rainfall occurs. The concept of heat drought becomes relevant here. Even in regions where precipitation doesn't decrease significantly, rising temperatures can create conditions of severe water stress because the evapotranspiration demand of plants and soil increases. This directly affects agriculture, reducing productivity even in years when rainfall is within the historical average. There's an apparent paradox in climate change that confuses a lot of people. How can a warming planet have more flooding and more droughts at the same time? The answer lies in the redistribution of water. Warming increases evaporation, putting more water vapor into the atmosphere. More vapor means more fuel for storms, more intense rainfall, and more concentrated precipitation events. But that vapor concentrates in certain regions while others become drier. The result is an intensification of extremes in both directions. When it rains more intensely and over a more compressed period of time. When it doesn't rain, dry spells are longer and more severe. Systems designed to store and distribute water throughout the year face both flood peaks that exceed their capacity and drought periods that drain their reservoirs. The water infrastructure of much of the world was designed for a climate that is ceasing to exist. As you rest, your thoughts becoming lighter, more distant, simply observing. Wildfires have become a global phenomenon of growing scale. Warming creates conditions of high temperature, low humidity, dry vegetation, and strong winds that make fires easier to start, harder to contain, and more destructive when they occur. These conditions, which historically were concentrated in certain seasons, are expanding into parts of the year and regions that were previously relatively protected. The Australian megafires of 2019 and 2020 burned more than 18 million hectares and killed approximately 3 billion animals. California, Siberia, the Amazon, and the Mediterranean have been experiencing progressively more severe seasons. The smoke from these fires can travel thousands of kilometers, affecting air quality and human health in regions far from the original source. A particularly important detail is that fires in peatlands, such as the vast peatlands of Siberia and Indonesia, can, when ignited, emit quantities of carbon comparable to the annual emissions of entire countries. And unlike a tropical forest that can regenerate in decades, a burned peatland takes centuries to rebuild its carbon stock. The polar jet stream is a high-speed air current that circulates around the northern hemisphere at high altitudes. It's driven by the temperature difference between the cold Arctic and the warmer temperate regions. As the Arctic warms more rapidly, the difference shrinks, and the jet stream becomes weaker and more meandering, making wider, slower curves. When the polar jet stream dips further south, it can push cold Arctic air into regions that normally have temperate climates, causing extreme cold waves in the middle of winter in places like the central United States or Europe. This pattern creates a distribution of climate extremes that can seem chaotic but is actually a logical consequence of the differential warming between the Arctic and the lower latitudes. This dynamic also contributes to what meteorologists call atmospheric blocking. Situations where weather patterns get stuck over a region for days or weeks, instead of moving normally. It's this kind of blocking that turns a 3-day heat wave into a 2-week one, or that keeps a rain system over the same region long enough to cause catastrophic flooding. Earth's biodiversity is under pressure from climate change in ways that go beyond the direct elimination of habitats. Warming alters the conditions that define where each species can survive: temperature, precipitation, seasonality, food availability. This forces geographic shifts that aren't always possible, and when they are, they frequently create new ecological tensions in the destination habitats. The key concept here is the climate niche, the set of conditions within which a species can reproduce and survive. As the climate changes, these niches shift toward the poles or to higher elevations. Species with high mobility can follow that shift. Species that are sedentary, specialized in specific conditions, or living in habitats fragmented by human activity often find themselves trapped in regions whose climate is becoming unsuitable for them. The result is what ecologists call extinction debt. Many species that still exist today are already, in climate terms, living in conditions incompatible with their long-term survival. They haven't disappeared yet because ecological processes have inertia. But the clock is ticking. And there's a detail that changes everything when it comes to coral reefs. Although reefs cover less than 1% of the ocean floor, They support approximately 25% of all known marine species at some point in their life cycle. They're ecosystems of extraordinary complexity and biological productivity, built over millennia by microscopic organisms called coral polyps. Corals live very close to their upper thermal limit. When water temperature rises just 1 to 2 degrees above the summer average for extended periods, corals expel the symbiotic algae that live in their tissues. These algae are responsible for both the vibrant color of the coral and for providing up to 90% of its energy. Without them, the coral turns white and becomes vulnerable, a phenomenon called bleaching. If temperatures don't return to normal quickly, the coral dies. If global warming reaches 2 degrees Celsius above pre-industrial levels, scientific projections indicate that between 70% and 99% of the world's coral reefs will be functionally destroyed. Not damaged. Destroyed. Your breathing is growing softer now, the weight of your body becoming lighter against the pillow, just resting. Tropical forests are the most biodiversity-rich terrestrial ecosystems on the planet and also the most important carbon stores at a continental scale. The Amazon stores between 150 and 200 billion tons of carbon in its biomass. For decades, scientists monitored it as a net carbon sink, absorbing more CO than it emitted. But that's changing. Studies published in the last decade show that parts of the Amazon, especially the most deforested and degraded regions, have already become net carbon sources, emitting more than they absorb. This is happening through a combination of direct deforestation and climate stress on the remaining forest, which increases tree mortality and reduces photosynthetic capacity. The forest is responding to decades of fragmentation and warming with a gradual loss of resilience. The most concerning concept in this context is the Amazon tipping point, a threshold beyond which deforestation and warming combine trigger a process of progressive savanization that becomes self-sustaining. Some estimates place this threshold at around 20 to 25% total deforestation, and accumulated deforestation is already at around 17 to 20%, depending on the methodology used. The proximity to this threshold makes political decisions about the Amazon over the coming decades extraordinarily consequential, not just for Brazil, but for the global climate system. Spring is arriving earlier. That might sound like a harmless observation. But for ecosystems, it's a profound disruption. Many organisms calibrate their reproductive and developmental cycles by day length or accumulated temperature. When different species within the same ecosystem respond to warming at different speeds, the timing relationships that evolution built over thousands of years can fall out of sync. The phenomenon has a name: phenological mismatch. A classic example comes from Europe. Certain migratory bird species arrive at their breeding areas at the same time as always, because they regulate their migration by day length. But they find the peak abundance of caterpillars, which they depend on to feed their chicks, already passed. The caterpillars emerged earlier in response to warming, but the birds can't adjust their arrival at the same pace. This kind of decoupling is being documented in ecosystems around the world. Between pollinators and plants, between predators and prey, between parasites and hosts. It's one of the most subtle, and at the same time most far-reaching, ways in which climate change is reorganizing life on Earth. Global food security is one of the most directly threatened dimensions. For each degree Celsius of warming above current averages, studies estimate that wheat productivity falls by around 6%, corn by approximately 7%, and rice between 3% and 8%. In a context where food demand is projected to grow alongside warming, these reductions represent a logistical and humanitarian challenge of great magnitude. The regions that will suffer the greatest reductions in productivity are precisely those that have historically contributed the least to emissions and have the least economic capacity to adapt. The tropical and subtropical belt, which includes much of sub-Saharan Africa, South Asia, and Central America. The geographic distribution of agricultural impacts is one of the most painful asymmetries of this crisis. What almost no one realizes is that the water question is inseparable from the food question. About 2 billion people already live in conditions of water stress. And climate change is reorganizing the distribution of water in ways that threaten the supply of entire populations. The problem isn't just the total amount available, but its distribution over time. Rainfall that's more concentrated in short periods and more prolonged droughts make it much harder to capture and store water efficiently. Climate migrations are often presented as a future phenomenon. But they're already happening. Populations in low-lying coastal areas, vulnerable islands, expanding arid zones, and areas subject to recurring extreme events are already on the move. The World Bank estimated that without significant climate action, up to 216 million people could be internally displaced by climate causes alone by 2050. What makes these migrations particularly complex is that they often don't fit the existing categories of international protection. Refugee status was created for people fleeing persecution and conflict, not environmental phenomena. People who leave their land because of rising seas or extreme climate events generally have no international legal recognition, leaving them in a legal gray zone without formal protection. As your body rests deeply, and thoughts drift further away like clouds moving across the sky, let there only be the feeling of being safe, here, now. Human health is affected by climate change through pathways that go far beyond direct heat. Warming is expanding the geographic range of disease vectors. Mosquitoes and ticks that carry malaria, dengue, Zika, and chikungunya are spreading to higher elevations and further north. Populations that have historically not been exposed to these diseases have little or no acquired immunity. Dengue is an illustrative example. In recent decades, it has advanced into Mediterranean European countries, to higher elevations in the tropics, and into parts of North America that were historically out of its reach. It's estimated that with 2 degrees of global warming, more than 1 billion additional people will be exposed to the risk of dengue compared to current levels. Cities are particularly vulnerable environments to climate warming because of a phenomenon called the urban heat island. The concentration of impermeable surfaces that absorb and retain heat, combined with the scarcity of vegetation that normally cools the environment, makes temperatures inside cities consistently higher than in the surrounding rural areas, often between 3 and 8 degrees Celsius higher on summer nights. This differential adds to the background global warming, making extreme heat episodes in cities even more severe than regional average data would suggest. Dense cities in tropical and subtropical countries, which already operate near the limits of human heat tolerance, face the risk of reaching conditions that make outdoor work genuinely dangerous during parts of the year. Global infrastructure was designed based on climate assumptions that are rapidly becoming obsolete. Bridges, dams, power grids, sewage systems, roads, and airports were all built to withstand conditions based on the historical records available at the time of their construction. As climate change pushes extremes beyond historical limits, this infrastructure faces stresses it was never designed for. Power transmission grids designed for historical maximum temperatures fail during heat waves that exceed those limits, at exactly the moment when demand for air conditioning peaks. Drainage systems become overwhelmed by precipitation events that exceed their design parameters. Asphalt roads soften and deform in extreme heat. Railway tracks expand and buckle. The cost of adapting or replacing this infrastructure is immense. And most countries don't have a systematic plan to do it. The benefits of adaptation have returns over decades, while the political costs are immediate. The result is that much of the adaptation that will need to happen will occur reactively, after disasters, rather than proactively. The Earth's climate system isn't a passive machine that simply responds proportionally to the forces acting on it. It contains internal mechanisms that can amplify or moderate ongoing changes. They're called climate feedbacks. And the distinction between those that amplify and those that moderate is fundamental to understanding why global warming is potentially more dangerous than a surface reading of the numbers might suggest. A positive feedback, in scientific vocabulary, doesn't mean something desirable. It means a self-amplifying mechanism. When warming causes a change that produces more warming, which produces more change, which produces more warming. The ice albedo feedback is the most direct example. White ice reflects most solar radiation back into space. When it melts, it exposes dark surfaces that absorb far more heat, which warms the environment more, which melts more ice, and so on. The water vapor feedback is the most powerful of the identified positive feedbacks. When the temperature rises, more water evaporates, increasing the concentration of water vapor in the atmosphere. Water vapor is a powerful greenhouse gas, and more water vapor means more heat retention, which raises the temperature even further. This feedback is estimated to roughly double the warming that would be caused by the direct increase in CO alone. Clouds are the greatest source of uncertainty in climate projections. They can function as both positive and negative feedbacks, depending on their type, altitude, and distribution. Low, dense clouds have a strong cooling effect, blocking solar radiation. High, thin clouds efficiently retain infrared radiation, producing warming. The central scientific debate is, how will global warming change the balance between these two types? The concept of a climate tipping point describes a threshold in the climate system beyond which a change becomes self-sustaining and potentially irreversible. The idea that the climate system can have distinct states of equilibrium, with abrupt transitions between them when certain thresholds are crossed. The tipping points identified by scientists include the collapse of the Greenland ice sheet, the destabilization of West Antarctica, the mass die-off of coral reefs, large-scale permafrost thaw, critical weakening of the Atlantic Ocean circulation, and the transition of the Amazon to savanna. Each of these systems, once disturbed beyond a certain threshold, tends to keep changing through its own internal dynamics. What makes this question especially concerning is the possibility of cascading effects. The accelerated melting of Greenland weakens the ocean circulation, which alters precipitation patterns in the Amazon, which increases stress on the forest, which pushes the forest closer to its own tipping point. Climate systems aren't independent. They're interconnected in ways that can transform a series of gradual changes into a systemic transition that is much faster and more profound. And there's a detail that changes everything about reversibility. In principle, if emissions were reduced to zero and carbon removal technologies were deployed at large scale, concentrations could gradually decline. Temperature would respond to that reduction. But reversibility is neither symmetric nor complete. The sea level rise committed by glacial melting will continue for centuries, even if temperatures stabilize. Extinct species don't return. Destroyed ecosystems may take millennia to reconstitute, if they ever do. And systems that have crossed tipping points may remain in their new state for very long periods, regardless of external conditions. One of the most important, and least known to the general public, concepts in climate science is the carbon budget. The total amount of CO that can still be emitted globally before warming surpasses a given threshold. This budget is calculated based on the approximately linear relationship between cumulative CO emissions and global warming. At current global emissions of around 40 billion tons of CO per year, the budget for keeping warming below 1.5 degrees with a 50% probability would be exhausted in less than a decade. That concrete number is what underpins the urgency that climate scientists express. It's not abstract alarmism. It's straightforward arithmetic applied to a physical system with well-understood behavior. As you keep breathing slowly, feeling the weight of your body sinking gently into rest, there's still so much more to explore in this story. Climate science is often presented as a set of predictions about the future. But most of the scientific work isn't about predicting the future. It's about understanding the present and the past with enough depth that future projections can be reliable. Climate models are tools of understanding before they are tools of prediction. Modern climate models are computationally extraordinary constructions. They integrate the physics of the atmosphere, the oceans, ice, vegetation, and the carbon cycle into a single mathematically coherent framework. The most advanced models run on supercomputers and require months of processing time to complete simulations of a century. What's important to understand about these models is that they are not tuned to reproduce specific climate trends. They are built from fundamental physical principles and then tested against independent observations. When a model developed from basic physics correctly reproduces the observed warming, the simultaneous stratospheric cooling alongside tropospheric warming, the polar amplification, and the patterns of change in global precipitation, that's not coincidence. It's evidence that the model captures the actual mechanisms of the climate system with sufficient fidelity. The Keeling curve, the series of continuous atmospheric co-measurements started by scientist Charles David Keeling in 1958 in Hawaii, is considered one of the most important datasets in the history of environmental science. When the measurements began, the concentration was approximately 315 parts per million. Today, it exceeds 420 parts per million. An increase of more than 30% in less than 70 years. What the Keeling curve reveals beyond the upward trend is a seasonal pattern that overlays the long-term trajectory. Concentrations rise in the fall and winter of the Northern Hemisphere, when plants are dormant, and fall in spring and summer, when vegetation resumes photosynthesis. That seasonal oscillation is, literally, the planet breathing. The detection and attribution of global warming to human causes uses an approach that compares the observed warming patterns with the patterns that different forcings would produce according to physical models. The most robust result of this analysis is that the observed warming pattern is consistent with the signature of greenhouse gases and inconsistent with the signature of solar variations. If the warming were caused by the sun, for example, we'd expect to see warming in both the troposphere and the stratosphere. What we observe is tropospheric warming and stratospheric cooling. Exactly the pattern predicted by greenhouse gas forcing. This climate fingerprint is one of the most direct pieces of evidence for the human origin of current warming. Paleoclimatologists, Scientists who study the climate of the geological past provide an indispensable perspective. Ice cores extracted from Antarctica and Greenland preserve bubbles of atmospheric air and allow us to reconstruct temperature and atmospheric composition over hundreds of thousands of years. The longest core extracted to date covers 800,000 years of climate history. It clearly shows the glacial cycles, the synchronized variations between methane, and temperature, and the relationship between atmospheric composition and climate across multiple independent cycles. When the past and physics both point in the same direction, scientific confidence becomes much more solid. The transition to renewable energy is the most important component of any decarbonization pathway. But the speed and scale required are frequently underestimated. To keep warming below 1.5 degrees Celsius, global emissions need to fall by half by 2030 and reach net zero by around 2050. A transformation of the global energy system in less than 3 decades, at a scale that has no historical precedent. The progress of recent decades is real and impressive. The cost of solar energy fell by more than 90% between 2010 and 2023, making it the cheapest source of electricity in history across much of the world. Wind energy followed a similar trajectory. But there's a crucial distinction. Electricity represents only about 20% of total global final energy consumption. The other 80%, used in heavy transport, shipping, aviation, high-temperature industry, and heating, is far harder to electrify directly. Most climate scenarios that project limiting warming depend on some level of carbon removal from the atmosphere in the second half of the century. Not because removal substitutes for emission reductions, but because it's unlikely that emissions will reach zero in sectors like aviation, agriculture, and certain industrial processes. The carbon capture technologies that exist today capture still minuscule quantities compared to annual global emissions. But their development trajectory is considered a scientific and industrial priority. Climate geoengineering is one of the most controversial topics. The most studied approach is the injection of stratospheric aerosols to reflect part of the solar radiation. The idea has natural inspiration in volcanoes. The problem is that it doesn't address ocean acidification. It would alter precipitation patterns in ways that would benefit some regions and harm others, and it would create a dangerous dependency. If the injection were abruptly stopped, the mass warming could manifest rapidly, in a potentially devastating shock for ecosystems. Climate justice is a principle at the center of international negotiations. The countries and communities that have contributed least to historical emissions are often the most vulnerable to the impacts of climate change and the least able to adapt. This asymmetry between historical responsibility and current vulnerability raises questions that have no technical answers. They require negotiation and value choices. The issue of loss and damage has emerged as one of the most contentious topics in recent climate negotiations. The 2022 Conference of the Parties was the first to formally establish a mechanism to address loss and damage, an acknowledgement that there are climate impacts that can be neither prevented nor adapted to, only compensated. The details of how this mechanism will work continue to be negotiated and reflect deep tensions over historical responsibility and international solidarity. Socioeconomic inequalities profoundly determine who suffers the most. At the local level, within any society, it's the poorest populations who live in the most vulnerable areas, floodplains, unstable hillsides, urban areas without tree cover, and who have the least resources to protect themselves, recover, or relocate. Ensuring that the climate transition is also a just transition, one that doesn't leave behind workers in fossil fuel industries, communities dependent on declining industries, or populations without access to low-carbon solutions, is one of the most complex political challenges of the climate agenda. Your breathing is becoming calmer and slower, and your thoughts are growing less distinct, softer, like the bottom of a still lake. The deepest frontier of climate knowledge isn't in the data or the models. It's in understanding how complex systems behave when pushed beyond their historical states. Earth's climate is a complex adaptive system, with multiple coupled components, nonlinearities, feedbacks, and thresholds that interact in ways the models only partially capture. This fundamental complexity means that there are aspects of the climate future that are genuinely uncertain. Not for lack of data or computing power, but because of intrinsic limitations on the predictability of systems of this nature. The risks that scientists call tail risks, low probability scenarios with extremely severe consequences, are the ones that most challenge both modeling and public communication. A collapse of the Atlantic Ocean circulation within this century. A large-scale release of methane from permafrost accelerated by feedbacks that are still poorly understood. A cascade of tipping points triggered by warming that exceeds certain thresholds. These scenarios aren't the central projections of climate science, but they are not dismissible either. And in managing risks with potentially catastrophic and irreversible consequences, prudence requires that low-probability, high-impact events receive attention disproportionate to their central probability. Just as we build levees to withstand events that occur once every 100 years, not just for the average flood. What is perhaps the most important contribution of climate science isn't any specific number. It's not exactly 1.5 degrees, or 420 parts per million, or 2050. It's the demonstration that the climate system is governed by comprehensible physical laws. That humanity is disrupting that system in ways without precedent in Earth's recent history. And that the choices made in the coming decades will determine the trajectory of the climate for centuries. That places current generations in a position of responsibility without parallel in human history. not because they're special, but because they're the first to have both the knowledge of the risks and the technical capacity to change them, and the last to have the time window needed to do so with any margin of choice. And as you let this story settle gently in your mind, notice that understanding the world is not a reason for anguish. It's a reason for attention, for care, for presence. The planet you inhabit has a history of 4.5 billion years of transformation. It has been through global freezes and through ages of heat we wouldn't recognize. And at every turn, life found a way. We are part of that story too. Not an accident. A continuation. And what we do with that understanding is what defines the next chapter. Let these thoughts dissolve now, like smoke fading into the night air. You don't need to hold on to any of them. There's nothing that needs to be resolved right now. Just rest. Just breathe. And as you drift into a deep and restoring sleep, remember to subscribe so these stories can keep finding you night after night. Sleep well, and sweet dreams.